So, thank you for coming to this talk about Elixir. Just to start to give an idea what the talk is about. So this talk is not about recipes for building distributed and fault-tolerant applications. Um, it's more of a talk how Elixir, when you write software in Elixir and also Erlang, how you approach it from a different mechanism, and you need to design your software in a way that you get things like concurrency, distribution, and fault tolerance as a consequence of your software design. So it's basically the idioms we have in the language that allows you to get those things as a consequence. And we are going to break this talk into three main parts. The first one is a very quick introduction, how Elixir came to be. The second one are about the idioms and how they are going to affect you, the developer. And the third part is what Elixir specifically is, because Elixir is a programming language that runs on the Erlang Virtual Machine. And as the Erlang Virtual Machine, as the JVM, has many languages that run in this virtual machine. So what Elixir is bringing to the table in this, from this perspective. Okay, and then if we have time, we can do a little bit of live coding, questions, and so on. So let's get started. So to talk about how Elixir came to be, a little bit of the history, we need to go a little bit back in time. I'm also in the Rails core team, the Rails web framework. And quite some time ago at this point, 2007 or 2008, we had a Rails 2.2 release. And one of the big things in this release was that Rails is finally thread safe. Okay, and the whole idea of being thread safe is the Rails core team knew that concurrency was becoming more and more important, right? So what they wanted is that you should get your Rails application, deploy it in a machine, and if this machine has 8 cores, it should be able to use all the cores. Okay, but the interesting thing about the word thread safe is that it's not about using all the 8 cores efficiently. It's about using all the 8 cores in a way that's not going to crash, right? It's like you can get your code, run with cores, and it's going to work, right? It's not going to crash. And so we had this in the release notes, and later I joined the Rails core team, and I kind of found out that this was a lie. Rails was not really thread safe because it's hard, right? How do you say that something is thread safe? You have a lot of Heisenbugs, you try to debug and then the bug's not there anymore, but when it's in production, it shows up. And because of many reasons, right? It was a very frustrating work to do. It was hard to debug, it was hard to think of good solutions, because the abstractions that we have here, they, when in most imperative object-oriented languages, they're not good to solve those concurrency problems. And so, I stopped and started to think to myself, if concurrency is becoming more and more important, right, or we're starting to have more and more CPUs, I need to find a good solution. And I knew that there is a category of programming languages that solve this problem really, really well. Right? Then I said, okay, I want to investigate. I want to go deeper. And then I started writing software in functional programming languages, study them, explore them. And they really make concurrency easier. Okay? And there are many reasons for that. And I think actually the following talk to this one is about immutability. It's going to cover some important aspects, right? But I would just want to focus on 2 right now, which is, first, in functional programming language, we typically have the state explicit, right? So when we're talking about object orientation, we have like objects to wrap around a state. And many of the concurrency issues, they come exactly, for example, you have 2 threads running different cores, for example, and they try to change the same place in memory, right? So you get a segmentation fault, things get corrupted, things not go as expected because 2 things are trying to go to that same place, okay? So, and it's hard to figure this stuff out because the state's hidden inside those objects, right? But if we start to treat the state more explicitly, it's easier to see. You see, oh, here's where I have state, and I can see that two things are possibly trying to change here at the same time, it gets much easier to reason about. So that's one step, right? But the most important step is that we even try to mutate things as little as possible. So instead of going, if I have an array, try to mutate that array in memory by adding an element, I don't do that. I think of transformations. I have an array, and then if I want to add an element to that, I get a new array. And then we start to work with data structures that are very good to work towards transformation instead of mutation. So this was really interesting. And when I got to this point and had this realization, I said, okay, this is a very good direction to go. It really felt, I identified exactly with those solutions because many of the problems that I was having when working with Rails was exactly because you're not following, right, those guidelines. And eventually, I continue exploring, I continue learning, and I found out about Erlang, okay? And I say that this is when I fell in love, okay? Who here is familiar with Erlang? Okay, good. So Erlang is a language created by Ericsson, and Ericsson is a telecommunication company. Erlang, at this point, is almost 30 years old, okay? And what makes Erlang really interesting is that when they designed the language as a telecommunication company, they had a very specific set of use cases in mind and requirements. So imagine that you're Ericsson, right? And you need to build a telephone switch, right? A telephone switch needs to be able to connect person A to person B so they can have a conversation. But you want a telephone switch to be able to handle as many connections at the same time, right? You want to install a telephone switch somewhere, and a lot of people are going to talk to their friends, to their family, all going through the same switch. So you start to have this idea of being able to handle, right, many connections concurrently, everything at the same time. And you also need to have, with telephone switches, you need to have this idea of distribution because sometimes you want to call your friend, but your friend is already talking to someone else through another switch. So the switches, they need to be able to exchange information and tell you, no, you cannot talk to that person, it's busy right now. So they also have this idea, it should be very easy for the switches to communicate to each other and have this idea of distributed setup of switches exchanging information, okay? And they have a bunch of other interesting ones. My favorite, the one I like to joke about, is that we don't receive phone calls, right, from our operator, cell phone operator, saying, hey, we're going to be in maintenance mode from midnight until 1 a.m., so please don't use your phone, right? We don't receive those kind of warnings. So they came up with the whole idea of how can you upgrade your code in production without bringing the system down. And we are going to explore a couple other consequences that you have when you're building software for the Erlang Virtual Machine, okay? But the thing is that they built this great virtual machine, and it was used mostly for telecommunication for a long period of time. And it was just about 2003, 2004 that people realized that this use case is very similar to this use case, right? Anything that's really running the network. So you have a server, and it can be a server that is doing video streaming. You have a lot of clients connected to that, and you need to send them the data, and sometimes you need to contact internal endpoints to get information, or web applications. Even more now that we are going towards the Internet of Things, right? You have a lot of different devices talking different protocols, and you need to be able to handle a lot of them at the same time. Okay, so people start, oh, so if it was good for telecommunication, it's probably very good for this use case too, and they're right. Okay, so we have companies like Amazon, Facebook that use the Erlang Virtual Machine in their infrastructure. Telecommunication companies like Ericsson and Motorola. Creston's not here, but I think it's about 40% of the 3G data in Europe goes through Erlang switches, right? Erlang machines. So that's really interesting. And we also have startups like Heroku. So if you ever deployed an application to Heroku, you use Erlang because they use Erlang in their routing layer. And we have even databases like Ryak. The Basho folks, they are here, can talk to them about it, that is implemented in Erlang. And so we have a bunch of people using it in production. And one of the very interesting of them, it's WhatsApp. They got acquired at the beginning of this year by Facebook by 19 billions or something. And throughout their history as a company, they always gave talks of how they are using Erlang in the infrastructure and how they are able to leverage Erlang as part of the infrastructure. And they wrote one of those was like how they got 2 million connections on a single node. So WhatsApp is an application that you install on your phone, and you can install on iPhone, Android, Windows, Nokia, whatever, and you can exchange, talk with your friends, create groups, and so on. So it's a messaging app. So they were talking about the infrastructure, and here, the interesting thing is that they were using a really powerful machine, right? This machine had 24 cores, 96 gigabytes of RAM. They're not using it. Just 40% of the machine resources was being used, but it's exactly the idea that we want, right? I want to build a software. It's going to run on my machine. It's going to use all the 4 cores on this machine right here. But when we put into production, it's going to be able to use those 24 cores in the machine in production as efficiently as possible, okay? And they have talks, or they say they got to some point up to 3 million connections on single machines. And one of the things that if you read the announcement or the news when they were acquired by Facebook, one of the things that everyone remarked is how their engineering team was actually quite small to handle all the load that they handled and still handled inside Facebook. So, so this is all very interesting, okay? And this is the introductory part of the talk, okay? So now you're wondering, okay, so how those companies are able to leverage Erlang to write those kind of applications, efficient applications that are distributed, run very well concurrently. So we are going to the part of idioms, right? So what are the idioms? What the language requires from you, and how should you design software? And to talk about this, we are going to go now into Elixir, okay? So Elixir is a programming language that runs on the same virtual machine of Erlang. So everything I said so far applies to Elixir, okay? And if you go to the website, you're going to see that Elixir is a functional programming language. But I don't like to stay with this description because Elixir is more than that, right? It's a concurrent programming language. And not only that, it's a distributed programming language. And this is very important because this is actually one of the reasons I fell in love with the Erlang Virtual Machine is because, to me, they are kind of solving the big problem, okay? They are like handling the big elephant in the room. Because if we go back 30 years ago when they were designing the virtual machine, they were not worried about concurrency. Nobody was worried about concurrency in the 80s, okay? Maybe some academics, but the industry in general, they were not. And what they wanted to do was actually to build distributed software. But when concurrency became more and more important, what they realized is that concurrency is a special case of distribution, right? Because when you have distribution, you have what? You have your code running in 2 different machines at the same time. But when you have concurrency, it's just a special case where everything happens to be running the same machine, right? They're not over the network. And then whoa, we can do concurrency really well too, right? So how can we leverage all that? So here, if you are programming in majority of languages, imperative, object-oriented, this is your code, right? You write a bunch of sequential code that's going to execute instructions. And the thing that's hard about threads is that we need to think about threads as interleaving of the sequential code, right? You have the sequential code, and then you need to think how you're going to interleave, how you're going to put the locks, all think in terms of this sequential code. And in Elixir, we also have sequential code, okay? But this sequential code is organized in very tiny things that we call processes, okay? And those processes, they're not operating system processes. They are virtual machine processes, and they are lightweight thread of executions, okay? So if you're talking about idioms, this is very important. We just learned a new word. We just added a new word to our vocabulary, which is process, okay? So those processes, they are very tiny, very lightweight, which means that we can have many of them, Okay, so when at the moment you start your Elixir node, you want to go to the shell, right, to type some commands. You already have like 50 processes running. Okay, and all those processes, they are isolated from each other, and the isolation gives us very interesting properties you're going to see next. So in the WhatsApp case, when they were saying they had 2 million connections. Each connection was one process, okay? So they actually had more than 2 million processes running at the same time in that case. That's how lightweight they are. You should not be concerned about creating hundreds, thousands of them, okay? So we create all those processes, they are isolated, and because they are isolated, we can have all of them running at the same time. So we start to get this idea of concurrency, right? Because if they need something to do, they just do whatever they need to do. They're all running at the same time. And every time you need to exchange information or do some kind of coordination, you do it by sending messages, right? So if I want to tell one process that it needs to do something particular or it's waiting for some particular input, I just send it a message, okay? So, we are talking now about processes. Is our new word. We are talking about message passing. And to learn more, let's zoom in. Let's pick like 4 processes and try to see what they are doing. Okay, and let's imagine that this is a server, right? It's doing something over the network. So those 4 processes that I chose, we can imagine that one is responsible for communicating with the database. Another one is responsible for accepting requests over TCP, so responsible for the network web part. We have a statistic process that is just keeping live statistics about who is using your application, who is connected, and so on. And we have a mailer process, okay, that is responsible to send an email every time you need to do something in particular. So here's the interesting thing. If you're using classical languages, right, imperative object-oriented, you have a request, and then you want to send an email during that request. What could actually happen that at the moment you are sending the email, if something goes wrong while sending the email, the thing that's responsible for accept requests can actually crash, can actually fail, right? So if we start to think about it, it's really, really weird. Like, why the thing that sends email, if that thing crashes, how can it bring the thing that's accepting requests down, right? So what we need to do in those languages is that we need to use try-catch, right? So if you go to your web server implementation in your language or the web framework, whatever, they wrap your code in a huge try-catch, begin rescue, and things like that. Why? Because if something goes wrong with the mailer, you just don't allow it to leak, allow it to go through and bring everything down. And and this whole idea, we like to say, oh, we should rescue an exception or catch an exception. This whole idea is weird, right? Because an exception is a way of a software to say something went wrong, right? Something supposedly exceptional happened, and you're just saying, thank you, just continue doing whatever you're doing, right? So it's a very weird idea, and when you start to put state with it also, basically what could happen is that you have your code running, it goes into inconsistent state, and then it starts raising exceptions, and so on, and you're just telling it to continue doing whatever it's doing. So in here, because everything is isolated, right, a crash in the mailer cannot bring any of those other things down. And that's a very important property because it changes the way you write software. What we like to say is that, if something is wrong in the mailer, just let it crash. I am told to not use the let it crash expression because sometimes it scares people, right? So we also say fail fast, okay? If something's not good with the mailer, fail fast. And what is going to happen is that we define supervisors, okay? So this is a new kind of process. It's a process that has a very specific responsibility of supervising other processes. So each process in different colors here, they're going to belong to different supervisors. So what happens is that if the mailer, something is wrong with the mailer and it crashes, this mailer, this process is going to die, and then the supervisor is going to notice that the mailer crashed and is going to start a new mailer to handle the next upcoming requests. Okay? So and this is very important because it starts to take us to this idea of building fault-tolerant applications. Because the thing is, it doesn't matter what you do, it doesn't matter whatever language you choose, things are going to go wrong, right? Unexpected things are going to happen. Even more when you include network, file system, kind of third-party resources, okay? So, instead of trying to be defensive and foresee all the possible cases, which we can't, we should plan for crashes, right? Instead of saying, I'm going to handle all possible cases, just let it crash and come up with a strategy for your system to self-heal, to go back to a state that's guaranteed to work. And that's why we have this whole idea of supervisors, because if something crashes, we start something new with the initial state that that it works. It's the same with our machines, right? Sometimes you're coding, and then our machine starts to get, not respond quite well, it's not working quite well. What do? We restart it, right? We go back to the initial state, and then suddenly it's good again, right? It's the same idea. Let's go back to that initial state. So if we're speaking about words, right, and the new words to our vocabulary and idioms, we are talking about processes, supervisors, and sometimes the supervisors, they have supervisors too, that may have a supervisor too. So we start to create those supervision trees, right? And at one point, your application is ready. You define the supervision tree with the responsibility on what should be restarted. And we package all of this inside an application. And an application is kind of a component, right? It's something that you can start and stop as a unit. So that's how we design software, and everyone writing Elixir code is how they're going to structure and design their software, okay? So what we have talked about so far, I talked about processes, which are isolated, okay? And we also have supervisors, which are processes that has this very specific responsibility of supervising other processes, and they have strategies on how they should react when something does not go as expected. And they are constantly putting our system back into this null initial state that's guaranteed to work. And then we define supervision trees, okay, and we package them inside applications. And every time we need to do communication, we always do it with message passing. And we got many features from it, right? That's kind of got for free from this design, right? So we got concurrency. Concurrency does not come as an afterthought, right? It's not like you write a source and then you need, I need to make it concurrent. And then you're like, now I'm making my code all ugly and messy just because I need to add concurrency, right? It's walking in Elixir, right? It's walking along with your design. It's a consequence of our design. So we are now getting concurrency. We are now talking about failing fast, okay? It's a different approach when we are designing the software. We got fault tolerance because we now have the supervisors with their strategies. And there is one thing, which is actually in the title of the talk, but we haven't talked so far, which is distributed, okay? We got all those things, but how do we get distribution out of all of this? So if we go back a couple of slides, right? We said that this is your Elixir software, okay? Running production, so have a bunch of processes, exchange messages, and for some reason, like part of application starts to have a increase in the load, right? Like you can have the statistics server, for example, for some reason it starts to have an increased load. So what you can do is that you can get your code, right? And we have something called the release process, where you can create different releases with different responsibilities. So you can get part of your code, right? And just say, I want to run this particular code in a different machine, right? So you just put in two machines, and everything's going to work. You just need to update the reference to say to whom you want to send the message, because since the processes, they all communicate with message passing. The virtual machine actually abstracts the message passing for you. So it doesn't matter if you're sending a message to this process in this machine or a process in another machine. It's all abstracted and handled for you. And we are going to see some examples soon. Right? I'll do a little bit of live coding and send messages between nodes so we can have a quick overview. So questions so far before we go into the third part. Okay, so Okay, so this is all interesting, right? And as I said, this is all properties of how the virtual machine was designed. So this not only applies to Elixir, but Erlang, Joxa, everything that's running in that virtual machine. So why Elixir, okay? Why would I use Elixir? And we have, and the best way to tell why you should go with Elixir when you're coming to this particular virtual machine and when you want to think about this particular kind of design of software, the best way to talk about it is to talk about our 3 goals in the language, okay? And they are compatibility, extensibility, and productivity. So compatibility is the easy one, right? It's just everything I talked so far, right? It comes from the virtual machine, and we are compatible. And all the abstractions, they are the same, whether if you're running in Elixir or if you're running in Erlang. So for example, a list in Erlang is a list in Elixir. A process in Elixir is also a process in Erlang. There is no conversion cost nor anything. So compatibility is about respecting this foundation of being distributed and fault tolerant, right? And you're not going to sacrifice that. That's what this goal is saying. The second one is extensibility. And the best way I like to describe extensibility is with this quote from Guy Steele. It's one of my favorite talks of all time. It's called Growing a Language. And at the end of the talk, he says, now we need to go meta. We should now think of a language design as being a pattern for language designs, a tool for making more tools of the same kind. Because the field of computer science, it got so wide that it is impossible for a language to, natively attack all those possible fields, right? So what we need to do is that we need to design a language that you as a developer, you can go and extend it and take it to the domain you're working on so you can really be productive. And the way we do that with Elixir is that we have a macro system that's very similar to how macros work in Lisp. So here is some Elixir code. So in Elixir, in many programming languages, you have if and unless, right? They are in many languages, they are keywords. They are something special that the language knows how to handle, how to compile to. And in Elixir, those things, they are just macros. They are implemented with Elixir itself, which basically means that if we are using Elixir to implement the majority of the features in the language, it means that you can also get Elixir and take it to the domain you're working on, right? We are not cheating. There are no special cases. All of those are in the core of the language. So what is the idea of a macro? A macro, for example, unless is a macro, it does not receive the evaluation of is number x, right? It's not going to evaluate if x is a number and return true or false. A macro is going to receive the representation of this code, right? So a macro is going to receive the code representation, and then it can transform this code to be something else. Since unless is the opposite of a if, is a negated if, that's exactly what we translate it to, right? We basically get an unless and transform into a negated if. So, and with this, we can extend the language and implement most of the language using Elixir itself. So some examples of what you can do with it, right? So here's how you would write a test case with Elixir. So we define a module called math test, and all your code in Elixir, it lives inside modules. And you can say, I want to use the XUnit case, which is the name of our test framework. And now you get these macros that allow you to express very elegantly what you are testing, right? So here's testing a very basic operation, and you're just asserting that 1 + 1 is equal to 2. And the interesting thing is, depending on the language you're using, you're kind of saying, no, don't do that, right? Because depending on the test framework you use, you should never call assert, because if something goes wrong, assert is going to say, hey, expected true but got false. You need to use things like assert equal, assert more than, assert match. You need to go into this specific API of unit testing. But in Elixir, you just use assert for everything, because assert is a macro, and as a macro, it can look at the code and say, I can see here that they're trying to compare 2 numbers. Okay? And when something goes wrong, it's going to give you a very nice error report, what you're trying to do, what is the left side, what is the right side, and why it failed. Because we can look at the code at compilation time and get information about it, translate it to other things. So this is one example. The other example is we have a library called ECTO, which allows you to write queries to run in a SQL database. So Elixir is a dynamic language, okay? But ECTO, it's actually is type safe. Okay, so if here the author is a string, but if you try to compare author with a integer, for example, the query would say, those things do not actually match, right? And we got a lot of inspiration from Link, from .NET. And Link is a language integrated query, right? It's part of the language. But here is implemented just using the language features, just using macros. And we can do a lot of we can extend the language, for example, to add type checking. We can ensure it's secure, so we're not going to inject something that can lead to a SQL injection. And it's also extremely efficient because in many cases, we can compile most of the query to SQL during compilation time, right? So you're not doing a lot of work at runtime. We just reduce the work we do at runtime is as little as possible. Okay, so those are all examples, and we can see many examples in the community, right, of people getting Elixir and extending to all those domains. And the third goal is productivity. And productivity is kind of hard, right, to explain. How do you say that a language is more productive than another? And so the way we like to describe productivity in Elixir is, about tooling, for example, or having first-class documentation. Because sometimes being productive is not always a language issue, it's a community issue, right? How can you get the community to all together write very good tools, right, with good APIs and good documentation? Okay, so there is a focus on documentation. I can show a little bit. We have very good tooling out of the box. So as soon as you install the language, you're going to get a good test unit framework. You're going to get a shell to start writing code. And we have this mixed build tool I'm also going to show. And lately, we got a package manager too. So if you start working with Elixir and someone already solved the problem that you want to work on, you just add one line to your file, and you're going to fetch the dependency, compile, and have it available for you. So if you want to use that ECTO code that compiles to SQL, you can just add it as a dependency and go work on your problem. Okay. So to show the things, let's actually do a very quick demo time. So what I'm going to do here is, as I said, when you install Elixir, you get, wait, that's not what you're supposed to see. I'm done. Yes. When you install Elixir, it comes with this build tool called Mix that allows you to create new projects, handle your dependencies, compile them, test them, and so on. So what I'm going to do here is that I'm going to create a new project called Foo. And one option that you can pass when you're creating a new project is the sub option, which tells it to create a supervision tree. So at the beginning, I was saying, we have the supervision trees that are inside applications. And I'm passing this flag just so we can gain some time. It's going to generate a supervision tree for us. So we run this command, it creates the code for us, and then we can just run something like mix test, and it's going to compile and run everything for us. One of the advantages of the Erlang Virtual Machine is a very fast boot time, so that's always nice. And OK, so let's take a quick look at the code that it generated. So you can see the project's really, really small. It comes with a config directory. So remember when I was saying that the runtime comes with this idea of applications, right? It also comes with the idea of how you're going to configure applications, which is really, really good because all the libraries in the language, they follow the same structure on how they are configured, right? You're not going to use a library and it's configured this way and another one's configured the other way. Everything is kind of standard, right? We have this idea of how you define applications and configure them. And we have a lib directory, which comes with a simple file, and the test directory. So let me remove the comments so we can focus on. OK, so here we define a module. Again, our code always lives inside modules. Can everyone see well in the back? So all of our code is defined inside modules, right? And I'm saying this module foo is defining an application. And what all an application needs to do is to define a start function that receives 2 arguments and start a supervision tree. So we are saying, no, here we are going to define our children. And in this case, we don't have anything yet, right? And we define what is the strategy for the supervision. So a one-for-one supervisor means that you can have many children, right? So one-for-one supervisor means that if one particular child dies, you just restart that one. But you can have, for example, things like one for all. If one of the child dies, you kill everything else and start them again. So there are different strategies that we can play with. And just to show a little bit how it works, let's do this. Let's define a worker, which is a task. And a task is just when you want to execute some particular computation, like send an email. And this task, we are going to define it with a module. OK, sorry. We are going to define it with a module, the module that we want to call. So in this case, I'm going to be a little bit lazy and say that the task is going to be defined the same module as my application. The function, it should call, so I'm going to go with do some work, and the arguments are not going to pass any argument in this case. Okay, so here I defined a supervisor that has exactly 1 child that is a task. So let's define exactly this task. So we have function, do some work. It doesn't receive any argument. And all we're going to do here is I'm just going to print start to do some work. And I'm going to sleep because just to simulate that we are doing some work. Okay, so if everything went well, what I can do now is that I can start my application. I'm starting it with a shell. And you can see that it printed, right? It started to do some work. And because we started the application, which started the supervision tree, which started the task that's starting to do those computations. And what I can do here is that our supervisor, it had a name. If we go back to the file, you can see that we gave it a name of foo.supervisor. This is just an identifier. It can be whatever you want. And I can ask, give me all the children for the foo supervisor. Right? And then it returns this information saying, well, what is the module, which is a task. This PID is this process identifier. Right? It's just identifying the process in case you want to send it messages and so on. And it's the type of a worker. And the 4th argument, we use it in case of code reloading. I'm not going to go into details. If you want to know more, we can ask later in the questions part or discuss later. So what I'm going to do is that I'm interested in this PID, OK? So I'm going to pattern match on it. I just want the PID. I don't care about the rest. Right? So I'm going to match on those things and get the PID out. And what I can do is that I'm going to send an exit signal to this process, saying that I want to kill it. And what happens here is that it just printed start to do some work again. Because I killed that process, and killing that process is a way that I am emulating failure, right? Imagine that that process was doing something, and then it crashed, something went wrong. And then the supervisor saw that process crash and say, OK, I'm starting a new one. And you can see that it started to do some work again. And the thing here is that if that process was sending an email, right, and something went wrong, that email, by default, if you don't add some kind of persistence, it's gone, right? But the idea is that your system always going back to that initial state and building on top a persistence layer, for example, to guarantee that the emails are always delivered is actually straightforward. And we have a couple libraries in the ecosystem that do that. But the important is all this idea of the supervisor restarting and going back to that initial state that's guaranteed to work. Joe Armstrong, the creator of Airlink, right? He says that they have systems at Ericsson that runs with 9 nines of reliability, which is, I think, is a second or microseconds being offline per year, right? Which is quite fantastic. Yes, we have time, so let me show something else that's really, really cool, what I'm going to do now is that I'm going to start a shell, right? The interactive shell, interactive Elixir, and I'm going to give it a short name. And when we give a shell a name, in this case a short name, it allows other shells or other machines that are running the same network to communicate. So I'm going to give this one the name of foo, and you can see that here it changed. It's showing right now the name of this node is foo@jv, okay? And I'm going to give this one the name of bar. So if I am in this shell here and I define a module like, I know this is a little bit cliche, but hello world that prints hello. You can see it defined the module on this shell, and then I can say hello.road, and it's going to print hello and return OK, which is the result of calling IOPut. So you can see that hello was printed here. But if I go to the other shell and type hello.road, it doesn't work, right? Because this module was defined just in the other one. It's not available here. But what I can do is that I can very easily spawn a process in the other node, right? I just say, I want to spawn a process in the node named foo@jv. And, oops. And what this process is going to do is to just execute this function, which calls hello.road. And when I run it, you can see that now it works. And the interesting thing is, there are two very interesting things here. The first one is that you can see that hello world was not printed here again, right? It's not printed twice. Hello was printed here. So what happens is that we started to execute the code in the other node, but the other node knows that this node is the one that triggered the request. So if you want to do any I/O, it's going to send back, right? And we use it in production because sometimes you have a machine that's not behaving well. You can do a remote shell. You can connect to it and send commands to it and try to get information on what is happening there, right? And you can see here that the PID, in this case, starts with a big number. The previous one always started with 0. So the one starting with 0 is running on your machine, and the ones that does not start with 0, they're running in other nodes, right? And I could get this PID and send a message to it and exchange information. Okay, let me go to the last slides, and then we can open for questions. So if you really found Elixir interesting, this is our website, and you can go to our Getting Started guide. Right now, we have two main guides. One is literally Getting Started is going to introduce you to the data types, how you do I/O, how you work with collections, and so on. And we have an advanced guide, which builds an actual application using those principles we kind of talked about here, and it's a distributed key value store. Okay, very small distributed key value store where you can have keys being stored in different nodes and so on. And if you're interested in seeing some actual use cases of people using Elixir in production, so we just released Elixir 1.0 kind of like 3 weeks ago. And 2 months ago, we had our first Elixir Conference in Austin. And we had a bunch of interesting talks and interesting conversations of people using Elixir for gaming applications, telecommunication services. There was someone talking about having a Bitcoin exchange server all built with Elixir. And so you can go to Elixir Conf and Confreaks and watch some videos. One of my favorite talks is a developer working at a game company, and they build a poker game, right? And the poker game lasts on average there 20 minutes, which means it's really, really hard for you to stop the system to upgrade it, right? Because when one game is in the middle, another one is starting, another one is finishing. So you don't have really a good time like for downtime, right? And people play the whole day, the whole night. So it gets tricky. And he was, in his talk, he was saying how they were using all these distributed aspects for running, for doing a hot coding upgrade, right? So they could upgrade their software live by using the distribution. And then he goes into how he designed the whole application. So in their case, each poker table is a process. Each player is a process, and they are exchanging information with the poker table. And when you're upgrading your code live, they basically move the poker table to another node, but still have the players here, so they have kind of a mixed setup. I really recommend it. It's really interesting. And we have plenty of books. If you go to the website, here are some of them. And I think at this point they were already updated to Elixir 1.0. And so we have plenty of resources. If if you start with the getting started guide and then say, oh, I want something deeper, right? There are different options you could choose from. We have screencasts being published. And that's it. I want to thank my company that allows me to work. At this point, I'm working full-time on Elixir for a year and a half. And really thankful because allow me to take the language to where we are today. That's it. Thank you. I have time for questions? Yep. Awesome.
It's a question from the audience, and it goes, what would happen to the faulty process when the supervisor starts a new process?
What would happen to the faulty process? It's just gone, right? So, so the question is, what's going to happen to the faulty process when the supervisor acts, right? So if you have something like I'm going to use one for all strategy as an example. So something crashes, right? And the other ones, because of the supervision strategy, it says you're going to kill the other one and restart everything again. It just kills them, right? It's just, whatever they're doing is going to be interrupted, it's going to cut, and they're gone. And the interesting thing is, so I was saying about, just to have an idea how this impacts also the design of the virtual machine and the language. The interesting thing is that because they're isolated, we don't have, for example, stop the road garbage collection, right? Because the process, they do not really share memory. And this is really good because if something is wrong and a faulty process, dies, the garbage collection just, goes and, okay, I got the memory back. You don't need to do any check. And it's really good for also the cases of WhatsApp, right? You have a connection per process. When that connection is gone because the client's connected or because you want to disconnect, you just reclaim it. You're not going to have a garbage collector going through all the 2 million connections at the same time to see if there's something shared and so on. Did I answer the question? If please ask more.
So I'm wondering about debugging. Is there something like, is there a meta layer? Like, can I look at one of those faulty ones and see what was wrong with it before it died?
So that's a very good question. What about debugging, right? When something goes wrong, what are you going to do? So I'm going to answer two different things. So the first thing is that we don't have traditional debuggers here because if you have a lot of processes running at the same time, right, and you say, I want to see what is happening there. When that process, you will say, stop, do a breakpoint to see what is happening there. Everything else, the whole road continues running, right? Nobody's going to stop for that particular process. So if you set a breakpoint in there, you can have other processes that were waiting for a message from this one, right? And then they're going to get a timeout because they don't get a reply. So we don't have a typical debugging system because at the point you're going to type what you really want to see, your system state changed completely, and then you're going to be debugging something you don't think really is there. So how do we work around that, right? The fact that we cannot use traditional debuggers. So very good tracing tools. You can basically trace any event that is happening in the virtual machine. A process started, a process crashed. I want to call this function. I want to see if this function is being called by this process with this particular argument. So that's one thing, and we ship with a very useful logging framework, and by default, all processes, they are going to log. I crashed, the last message I received was this was my particular state, and this is the stack trace. So we improve with those tools, and the nice thing is that the whole language came from from industrial setup, right? So they had to figure this stuff out, how to have a good logging and understanding of the system.
So I would traditionally set a breakpoint, and then I would inspect something and look into and write some expressions. So what it sounds to me is that I will need to do changes to my code, then get that code deployed, and do changes to my code to get that deployed. But you mentioned also that you can deploy code while the application is running. Could you tell something about, like, how would I if I need to change these logging statements a couple of times to get to figure out my problem, how would I?
Okay, so the question one is about the hot code loading and how we're doing production. So typically what it would do is that one machine is faulty, right? And you don't want to bring it down for some reason. You're going to log into this machine. You're probably going to start to do some tracing and try to see what is wrong. If the logs are not good, you could start with some tracing to see why the logs are not good, what exactly is happening there. And when you pinpoint, if you want, you can, you go to the tag in your source code, right, that had that particular version deployed. You can change that module, compile it, and tell the virtual machine to load this new version of the module. Okay, so that's a very simple idea of how it works. I don't think I have like time to show exactly how to do the setup to show how it would work, but I said like a couple times during the talk that all your code lives inside modules, right? And you cannot have code outside of a module. And the reason is because we use the module as the main container for code, because we also use it for upgrading the code in production. So you can see here that when we define the module, right, it returned a tuple saying, oh, this is a module, this is the name of the module. And you can see this whole thing with a bunch of gibberish here. This is a binary with the module bytecode. Okay, so for example, what I could do is that I could actually, let me see if I can do that. So yeah, it may not work, so don't hold me to it. So it's still hello.road is not defined here, right? So what I'm going to do is that, so if I get v1 is going to give me the contents of the first expression, which was that module being defined. So if I type v1, it gives me what was the value defined here, right? So we can see that we have the module, the name, and the binary. And I'm interested in the binary, so I want to pattern match on it just to get this binary. Okay, and this I'm going to match on v1. So now I have the binary here. So what I'm going to do is that I'm going to do an RPC call to the node bar at JV. Damn it, what are the arguments? It's called load binary. And I need to pass the module name, the file it was defined, and the binary. Let's see if this works. Oh, it worked. So now, if I go to the other node, hello road is here, right? So I started to sweat. So this is, for example, how you would do, right? There's a little bit more of more detail to that, but that's basically the idea. It can get the bytecode and send it to the virtual machine and say, hey, now what the virtual machine has, that it has two versions of the same module. It can have two versions of the same module memory. So you have the old one and the new one you just sent, and you can say to some existing code, say, I want you to upgrade to the new version, right? So this is kind of how you can do a live patch in a production system. Oh, we're out of time. Please ping me, and thank you.